Hello and welcome to our lesson on the chain rule. So the chain rule is another differentiation rule that we are going to use to find the derivative of compositions of functions. So we're going to take a minute to just review what that is, just to make sure we're all on track here. When we're looking at the composition of two functions, or what we call the composite functions, that composition of two functions, we'll call them f and g, can be denoted two ways. So you've likely seen this notation, and just to be extra clear, that was an open circle. And this means the same thing as this. And we are reading either of these as f of g of x. So f of g of x or f of g of x. You're going to read those parentheses or that open circle as the word of. But what this means is we have a function getting plugged into another. So in this case, we have this entire function, right, g of x getting plugged into f. And this means the same thing, it's just different notation, but g of x is getting plugged into f of x. So because g of x is plugged into f of x, we call f of x the outer function. So f of x is referred to as the outer function, or sometimes the parent function in the situation. And then g of x, the one that gets plugged in, it goes inside. We call that the inner function, or sometimes we can refer to it as the transformation of the parent. So let's take a second to see if we can recognize an outer versus inner function and how these are composite so that we can apply our chain rule and differentiate. So for example here, we have a linear function, this 2x minus 5, plugged into a quadratic function. So in this case, we would say our outer function, f of x, would be x squared, the squaring function, the quadratic function. And the inner function is the linear function, the 2x minus 5, that got plugged in. So that again, if I was to find f of g of x, if I was to take this linear function and plug it into my squaring function, then instead of x squared, I would have 2x minus 5 squared, which is exactly what we have here. Okay, so the composition of two functions. And then the chain rule is going to be a rule that we can use to differentiate. Now, it's not that we can't necessarily differentiate this already. If I was to multiply 2x minus 5 by itself, I could come up with a polynomial and use the power rule to differentiate each of the terms. So I actually already know how to take the derivative. I don't need a chain rule to do this problem. But if this exponent becomes something large, like let's say it's to the 10th power, I don't want to have to multiply that binomial by itself 10 times in order to use my power rule to differentiate. So the chain rule will definitely come in handy. Okay? So let's practice a couple more, just finding the outer versus the inner. So in this case, our outer function is our square root function. So I would say the outer function, the parent function, would just be the square root of x. And the inner function is the linear function that got plugged into that. So the inner function, g of x, would just be an x minus 7. So that again, if I was looking for the composition of these two functions, f of g of x, if I was to plug that linear function into that square root function, I would have not the square root of x, but the square root of x minus 7. Again, exactly what we have here, so that's a composition. All right, and then one more. In this one, I have a rational function, and my parent rational function, or my parent reciprocal function, is just 1 over x. That means in this case, switching colors when I don't have to, g of x, my inner function, is this entire quadratic here. So that would be x squared minus x minus 20. So that if I was looking for the composition, f of g of x, I would take this whole quadratic, plug it in here, and I would have the function I started with. So 1 over x squared minus x minus 20 is the composition of these two functions. Okay? So if we identify we have a composition of two functions, again, the chain rule is what we're going to use to differentiate. So the chain rule is a differentiation rule that applies to compositions of two functions. Now I have some steps here. They're not going to make a lot of sense, so let me show you the actual rule, and then I'll go back to those steps and hopefully they'll be a little bit more clear. So if we have a function, we'll call it y, that is defined by the composition of two functions. You have some outer, some inner. Then the derivative of y with respect to x, again, means we are differentiating with respect to x the composition of those two functions. So all of this is just notation. This tells us what we're doing. Here's the actual differentiation rule. So we're looking for the derivative of the outer function and ignoring the inner function, like here's our original inner function as is, and then we're going to multiply by the derivative of that inner function. Now already this seems kind of weird. How do we take the derivative of the outer function and ignore the inner function? Well, after you do it a few times, you'll actually really easily be able to ignore a function. But let me show you some steps that we can start with just to get the hang of the process. And then eventually, hopefully you wean yourself off of using these steps. So we're going to have some composition. I'm not really going to be worried about what our function is going to be named. I just want to think about the two functions that I have here, which one is the inner, which one is the outer. And what I'm going to do first is replace that inner function, whatever it is, I'm going to replace it with u. So instead of f of g of x, I'm going to be looking at f of u. And then I could take the derivative of f of u really nicely. So I'll be finding f prime of u here. Now I substituted u in, but ultimately we're trying to deal with this f of g of x. So after I differentiate my outer function, I'm going to replace u with g of x, which is what it replaced originally. So now I'm going to get u out of the picture and put g of x back in. That's going to give me, instead of f prime of u, f prime of g of x. And that is what we have here. This is the first part of our rule, f prime of g of x. So all I have left to do is multiply by the derivative of the inner function. So if I multiply that by the derivative of the inner function, if I multiply the f prime of g of x by the derivative of my inner function, g prime of x, then I'm done. That's going to be the derivative of that composition. Okay, so let's try it out. We're going to try to use the chain rule, try to use those steps to find the derivative here, again, because I don't want to necessarily cube this in order to use my power rule. So first, I'm going to replace my inner function, which I can see here is x squared plus 1. I'm going to replace that with u. So I'm going to say my outer function, f of u, is, instead of x plus 1 cubed, it's u cubed. Because that's really easy to differentiate. I can use my power rule here and call this 3u squared. Remember, multiply and subtract 1 from the exponent. So that's f prime of u, but I don't really want u. I want f prime of g of x. So f prime of g of x. Now I'm going to replace u with what it replaced. So I'm going to take u back out and I'm going to put x squared plus 1 back in, right? So my g of x is that x squared plus 1, it goes back in. So this is going to be, instead of 3 times u squared, 3 times x squared plus 1 squared. And then it's one more step. After we get this f prime of g of x, we need to multiply by the derivative of that inner function. So if I want the derivative of my inner function, g prime of x, really easy. I can use my power rule here too. So the derivative of x squared will be 2x, and the derivative of the constant is 0. So g prime of x is just 2x. So my final step here is to find f prime of g of x, again, and multiply it by g prime of x. That's going to be my derivative. So we're going to have 3 times x squared plus 1 squared multiplied by that 2x. And I can go one more step here because this is really easy to multiply. So I'm going to say that my final result is 6x times x squared plus 1 squared. And that is the derivative of what we called y with respect to x. So I'm going to put that notation in here, and we're good. There it is. That is the derivative of y with respect to x using the chain rule. Okay? So that might feel like a bit much. Let's try it again, and hopefully after a few more you'll wrap your brain around it if you haven't got there yet. So I recognize this is a composition. I have a linear function plugged into something to the 5/3 power, a power function. So the first thing I'm going to do is replace my inner function with u. So I'm going to rewrite this as f of u. So instead of 2x minus 5 to the 5/3, it's u to the 5/3, because that is easy to differentiate. So f prime of u gives me 5/3, we multiply, and then subtract 1 from the exponent. So 5/3 minus 1 would be 5/3 minus 3/3, which is 2/3. That's going to be my exponent here. Okay, now that's f prime of u, but I don't really want f prime of u, I want f prime of g of x. So now I'm going to replace u with g of x, which is my 2x minus 5. So here f prime of g of x means get u back out and put g of x back in. So instead of 5/3 times u, 5/3 times 2x minus 5 to the 2/3 power, and then just one more step. I have to take that and multiply it by g prime of x, the derivative of that inner function. Well, the slope of my line here is just going to be 2. And so final result, f prime of g of x multiplied by g prime of x is 5/3 times 2x minus 5 to the 2/3 power times 2. And again, easy enough to multiply here. So we're going to call this 10/3 times 2x minus 5 to the 2/3. And technically, this is f prime of x. And we're good. We're done. That is our derivative of our composite function. Okay? Now, it seems like a lot of steps. I do not take this many steps when I'm doing this process, and hopefully you're already seeing how you could shortcut this, but this work of replacing the u, or the inner function with u, and then putting that back in, these to me are 3 steps that aren't necessarily steps we have to take. Let me just show you. So if I was doing this, I would go right to finding my derivative, and I would just see this in my head as, okay, if I was taking the derivative of u to the 5/3, I would multiply by 5/3 and subtract 1 from the exponent to give me the 2/3. And then I've got u in there, but I know it's going to get replaced. Well, I don't need to do the rewriting. I can just leave 2x minus 5 alone, and then multiply by the derivative of that inner function, so multiply by 2. So all I really have to do is take these last 2 steps, if you can do some of that in your head, if that makes sense, okay? So let me try to show you on the next one, and if it's a complete fail, we can go through the steps again, but hopefully we can work smarter and not harder. So we're trying to take the derivative with respect to x of this square root function. Now in this one I would actually take a step first. I would rewrite this. Much easier to differentiate something that's raised to a power. So I'm going to rewrite this as x plus 5 to the 1/2 power. Remember, the square root is the square root of this thing to the first. So we can write that with a rational exponent. So then I can, again, use my power rule here, basically. So I'm going to pretend in my head that this inner function is just a u. So if I was differentiating with respect to x, then I would multiply by 1/2, and then I would subtract 1 from my exponent. So 1/2 minus 1, or minus 2 over 2, would be a negative 1/2. That's going to be my negative, or that's going to be my new exponent, so negative 1/2 here. And then normally this is a u, and then I put back in x plus 5. I'm going to skip those steps and just say, okay, this needs to be x plus 5 here. So I take the derivative of my outer function and ignore my inner function, just leave it in there. So use my power rule out here and leave that inner function alone. And now multiply by the derivative of my inner function. Well, the derivative of my inner function here is just going to be a 1, so I multiply by 1. So then I'm almost done. I just need to clean this up. So multiply by 1, that's not going to have any effect, but I don't want to leave a negative exponent, so I'm going to move this x plus 5 down to the bottom of the fraction with the 2, make that a positive 1/2. And at the rational exponent is fine, but because we started with a radical here, we should probably write this in radical form. So I'm going to go one more step and call this 1 over 2 times the square root of x plus 5. And that would be our derivative with respect to x, using our chain rule, but not having to go through all of those steps. Okay, so let's try again, finding this derivative without having to go through all of the steps. So my inner function, what we need to be visualizing here as u, that's this x squared plus 3. So imagine it's 3u squared that we're trying to differentiate. So we're going to say g prime of x, our derivative, would be 2 times 3 is going to be 6. And then remember, we're just ignoring this thing in the middle. We're going to leave it here. Subtract 1 from the exponent. Now we're here. So if it was just 3u squared, it'd be 6u, and then we'd replace u with x squared plus 2, so let's just skip that, right? Now we got to remember, multiply by the derivative of the inner function. So the derivative of x squared plus 2 would just be 2x. And then I can take one more step here, again, because it's easy enough to just multiply. So we're going to make this 12x times x squared plus 2. And again, this is still easy to multiply because this is to the first power. So I'm going to go one step further here. And this would be an okay answer, but because, again, it's simple enough to multiply, I'm going to go ahead and make this 12x cubed plus 24x. And there's our derivative. Okay, hopefully that's making sense. So pretend that it's 3u or 3x squared. Take that derivative, but leave that u, that inner function, intact, and then multiply by the derivative of that inner function. All right, let's try with some that are a little bit more complicated. I don't know, maybe this one's not so bad. So we're going to find the derivative of y. We can call it y prime or dy dx. I don't know that I've used the y prime notation, but that's totally fine. So let me just go over here. So y prime, again, this is my inner function. So imagine it's just u to the 4th. So I would multiply by 4 and then take 1 away from the exponent. But it's not u, it's x squared plus 3x. Okay? So there it is. Now we multiply by the derivative of the inner function. So that's going to be a 2x here. And then this is going to be 3 here. So the derivative of the inner function would be 2x plus 3. Now this would be a totally acceptable way to leave the answer, although I probably would multiply the 4 into this binomial just to make it a little bit cleaner. So I'm going to call this 8x plus 12 multiplied by this x squared plus 3x cubed. And I would not go any further with this because this is just unnecessary work cubing that binomial. It's not going to make things look any better. In fact, it probably makes it look a little bit worse. And if you wanted to leave the answer in this form, that would be totally fine too. All right, so there it is. Let's try another. Differentiate with respect to x. So we're going to look for y prime. Got to see what the parent is in here. Actually, I'm going to rewrite this function first. So maybe in your head you're thinking, all right, this is a quotient. We could use a quotient rule, and that eventually would totally be fine. But if I can avoid using extra rules, I would. So I'm just going to move this to the top of the fraction by changing the sign of my exponent. So I'm going to rewrite my function as 5 times x plus 1 to the negative second. That way, using my power rule becomes very simple. So now I'm just going to envision this as my u. So when I go to find y prime, the derivative of y, if it was 5 times u to the negative second power, I would multiply here to get a negative 10. I would leave u alone, and then I would subtract 1 from the exponent. And then once I've done that, multiply by the derivative of that inner function, derivative of the inside, which would just be a 1. So then we clean this up. Multiply by 1, not going to do anything, but I'm going to move that back now to the bottom of the fraction so that I can make that have a positive exponent because it's more proper, and then we're done. There's our derivative. So take the derivative of the outer function, right, ignoring that inner function, just leave it there, and then make sure to multiply by the derivative of that inner function, and you've got your chain rule. Okay? Now sometimes it is an ugly process, and that's precisely what's going to happen here. So we're looking for the slope of the line tangent to f of x. That's still just finding the derivative. But our inner function is going to require the quotient rule. So just brace yourselves for this one. It gets a little messy. Okay, so let's envision this whole thing, this whole inner function, this whole fraction, that's u, right? So if I was looking for f prime of x, I'm taking the derivative of the outer function u squared would be 2u to the first, right? So it would just be 2, not u, but 3x minus 1 over x squared plus 3 to the first power. Okay, so that's the derivative of my outer function, ignoring my inner function. Well, now I can't ignore it, right? After I do that piece, I need to multiply by the derivative of that inner function. Well, the derivative of the inner function is going to, again, require the quotient rule. So the derivative of u requires the quotient rule, which, if you recall, is fg minus fg, derivative, and g squared. So this is the format where, oh, I should have changed colors here. Let me do that again. So fg minus fg and g squared, where the numerator is our f and the denominator is our g. So lots of f's and g's in two different things, but we need to multiply by the derivative of this inner function, so that's going to require that quotient rule. So let's do it. We're going to do f prime first, so the derivative here would just be 3, multiplied by the denominator there, which is x squared plus 3. Then we're going to subtract f, which is 3x minus 1, multiplied by g prime, that's going to be 2x. And then we're going to divide by g squared, so x squared plus 3 squared. Alright, now in reality, if you left it like this, it's not wrong, but I probably would at least simplify this and probably multiply here as well, because that's easy enough to do. So let's say f prime of x is equal to, again, I'm going to go ahead and do this. Remember, that's 2 over 1. So I'm going to make that 6x minus 2 over x squared plus 3, and that is being multiplied by 3x squared plus 9, and then negative 3, let me do this, make this negative, so a negative 6x squared, and then a positive 2x, and that's going to be over x squared plus 3 squared. Now again, this would totally be fine for an answer, but I'm going to go ahead and take this one more step and make one fraction, because those denominators are kind of nice. I can make this a little bit more concise. So final answer, I'm going to say f prime of x is, this was f of x, yep. In the numerator, I have a 6x minus 2, which I don't feel like distributing, so I'm not going to, but I can combine these, so that's going to be a negative 3x squared, and then a positive 2x and a plus 9. If you wanted to take another step to multiply those, you could, but it's totally not necessary. Now on the bottom, I have an x squared plus 3 here, multiplied by 2 more factors of it there, so I end up total with an x squared plus 3 to the third power. And this is probably where I would stop, although again, all 3 of these would be correct forms of the answer. Okay? So it's the derivative of the outer function, leaving the inner alone, and then multiply by the derivative of the inside. Alright, let's try that again. So here, I have 2 things happening. I have an outer function of a square root function, an inner function of 1 minus x squared, but this is the product of 2 functions, which means I'm going to have to use my product rule to start here. So, excuse me, let me do one more, rewrite this again. The square roots you can leave in there, it's just much easier to work with exponents. So I'm going to rewrite this as 1 minus x squared to the 1/2 power, but I still need to use my product rule. So let's call this f and g. Remember, the product rule is fg plus fg, derivative. So if I multiply by the derivative of f, let's go here, so y prime, or dy dx, let me use my notation that it's asking me to use here. dy dx is going to equal So again, f prime, so the derivative of x squared would be 2x. That's going to be multiplied by g as is, so 1 minus x squared to the 1/2. And then I'm going to add f as it is, which is x squared, and that's going to be multiplied by g. Now g is this function, is this composition of functions. So when I go to find g prime, I have to use my chain rule. So g prime, using my chain rule, would be 1/2, right? I'm multiplying by 1/2, ignoring that stuff inside, and then subtracting 1 from my exponent, so 1/2 minus 1 is a negative 1/2, and then that gets multiplied by the derivative of the inside. So the derivative of 1 minus x squared, well, the constant's going to go away, and that's going to be a negative 2x. And I said it, but didn't write it. Okay, so g prime required the chain rule. And now I have this monstrosity to try to clean up a little bit. Okay, so let's try to do that. Let's try to clean this thing up. So this is, let's see, 2x times, I can go ahead and make this the square root of 1 minus x squared again, plus I have, let me leave this alone for a second. Inside the parentheses in green here, that chain rule piece, the 1/2 times the 2, that's going to make, times the negative 2 is going to make a negative 1x. And the 1 minus x squared to the negative 1/2 is going to go to the bottom. So that's going to become a 1 minus x squared here. And if I multiply here on the top, I'm looking at, let me just leave this alone again, 1 minus x squared. I'm going to make this a minus. I can make it plus with the negative on top, but just to be concise, the x squared times the x is going to make an x cubed over that square root of 1 minus x squared. So this ended up on the bottom of the fraction to make the 1/2 positive, and then I just rewrote the 1/2 as a radical again. Since I started with radicals, best to end with radicals. Now, this again would be an okay form of the answer. Might be better to get a common denominator and actually put the fractions together, although I would probably be okay with you stopping here. Now if we wanted to get a common denominator and add these, I would have to multiply here by the square root of 1 minus x squared. And so this becomes 2x times, if I multiply this here, the square and the square root, right? Squaring that thing is going to cancel that square root, so I'll have 1 minus x squared. And then I can bring over my other numerator because now we're going to have our common denominator, which is the square root of 1 minus x squared. And can we go, yep, let's go ahead and take this to the next step here. So this distributed is going to be a 2x, and then a negative 2x cubed, and then I still have a negative x cubed over that common denominator. And because I have like terms, one more final step. So negative 2x cubed and negative 1x cubed makes negative 4x cubed over my square root of 1 minus x squared. And that is my derivative of y with respect to x using the product rule and the chain rule. Okay, so we're starting to get into some real serious algebra here. Actually don't think that the calculus part of this is too terrible, although maybe it's all just terrible. I don't know how you're feeling about this on the other end of this screen, but hopefully it's manageable. And I don't know that they're going to get much worse than this, but hopefully you followed. All right, let's try this last one. So we're trying to use this function to basically go through the whole process of finding the derivative, finding it at a specific value, finding a point of tangency, and the equation for that line that's tangent to the curve, so like completing the whole process, not just finding a generic derivative that's, remember, just an equation to find slope. Now let's find it at a specific point. So I'm going to start by rewriting this function. Again, I don't like the radicals. If I don't have to leave them in there, I can make this x squared plus 4 to the 2/3 power. So finding the derivative means just using our chain rule. Fortunately, no product or quotient involved. So let's find f prime of x using our chain rule. Remember, let's visualize this as a u, or just an x. If that was just an x, we would multiply by 2/3, and then we would subtract 1 from the exponent, so 2/3 minus 1, which is 3/3, would be a negative 1/3. And if it was just an x, we'd leave an x in there, but it's not. It's an x squared plus 4, so let's leave an x squared plus 4 in there, and then multiply by the derivative of that x squared plus 4, which will be a 2x. So I'm going to go ahead and multiply here. So f prime of x is going to be a 4x in my numerator. And I'm going to have a 3 in my denominator, right? That's my 3. And then this is going to end up going to the denominator as well, because we want to make that exponent positive. So that's going to be x squared plus 4 to the positive 1/3. And again, I started with the radical, so I'm going to go ahead and rewrite this with the radical. So we're looking at 4x in the numerator, and 3 times the cube root of x squared plus 4 to the first in my denominator. Alright, so there's my derivative. That's the general formula or equation I could use to find the slope at any point tangent, or at any point along this curve. Okay, so what we want to do now in part B is find this derivative at 2. So we found f prime of x, that's our derivative. Now we want to find f prime of 2. What is the actual slope at that point, or at that x value? So f prime of 2, let's replace x with 2. So 4 times 2 in the top, and 3 times the cube root of 2 squared plus 4 in the bottom. So 4 times 2 is 8 in the top. This is going to be 3 times the cube root of 2 squared is 4. 4 plus 4 is going to be 8 in that cube root. And the cube root of 8 is 2. So this becomes 3 times 2, which is 6 in the bottom. And then that reduces to 4/3. Alright, so we have our derivative. That's the equation we could use to find slope. Now we have the actual slope at the x value of 2. Let's go ahead and find the point of tangency at x equals 2. So that's going to be a point where our x value is 2, and to find our y value, remember we're looking for a point that's on our original curve, so I need to find f of 2. That's going to be our point of tangency. So when I go to find f of 2, the original curve was the cube root of x squared plus 4 squared. So it's 2 squared plus 4 quantity squared. So that's the cube root of, again, 2 squared is 4, 4 plus 4 is 8, and 8 squared is 64, and the cube root of 64 is 4. So our point of tangency is at 2, 4. And now I gotta go up here and box this in. For some reason I started boxing things in. Was I doing that all along? Okay, I was. Alright, so then the last step of this process, this would be as far as we could take it. If we find a derivative, remember that's generic, find it at a point, that's a slope at that particular point, and we just found the particular point. Now let's actually write the equation of the line. So our equation of our line is going to be written using y minus y1 equals m times x minus x1, where this is m, this is x1, and this is y1. So we're looking at y minus 4 equal to the slope of 4/3 times x minus 2, and I'm going to run out of space. So y minus 4 equal to 4/3 x minus 8/3. And then I need to add the 4 over. So if I add 4 to both sides, then I end up with y equal to 4/3 x, and let's see, if I have a negative 8/3 and I add 4, then I have to multiply this by 3, so I'm adding 12 over 3. So 12 minus 8 would be positive 4/3 for my equation. Alright, now that's a lot of work, and I want to make sure I did it right. So I'm going to go ahead and use Desmos to confirm all of this. So I'm going to put in first my original function. So I'm going to put in the cube root, so if we go into the functions menu here and all the way down to the bottom, then we can get in a radical with any index. So there's our cube root of x squared plus 4 quantity squared. So there's our function, and now I'm saying that at the point 2, 4, just better make sure that's on my curve. It is. That this is the equation of the line that's tangent through that point. So let's type that in. Y equals 4/3. And let's make sure x is not in the denominator of that fraction. And then plus 4/3. And there it is. Exactly what we would want to see. There's our line tangent to that curve at that x value of 2. It's perfect. So thank God. Because what if we did all that work and I screwed it up? That'd be really upsetting. But we didn't. We survived. Okay? So there's, again, some serious algebra happening in some of these problems, but hopefully it makes sense. Should have enough to get going on your assignment, but if you need some extra help, please reach out. I am here to help. All right, until next time, take care.